Hi, I'm Jared. Welcome to Fun Science Demos. This is my good friend Mitz. He blows bubbles, and a bubble is nothing more than a thin layer of soap with air trapped inside. And air is a gas, and that's the big idea. What is a gas? Say hello to the crowd, Mitz. What do you notice? Well, the bubbles drop all the way down to the bottom of the tank. Through science, we've discovered that pretty much everything in the universe is either matter or energy. Now, we've talked about other forms of energy, light, heat, sound, and electricity in other videos. Today, it's matter. Through science, we've discovered that matter is made of stuff, and that stuff takes up space. And that stuff could either be a solid, a liquid, or a gas. Today we're going to talk about three types of gases. One type we make in our body, it's called carbon dioxide. Another type, it's in the air and we need it to live, it's called oxygen. The third type, it's in these balloons, it's called helium. Now all of those gases, they're different, but they're also alike. They're all clear, we can't see them, and we can't smell them, but they're there. So how do we prove it? Now all living things, including us, make carbon dioxide. But we can also make carbon dioxide using science. And what we're going to do is combine vinegar and baking soda to create the gas carbon dioxide. But we can't see it or smell it, so how do we tell it's there? That's where my good friend Mitt comes in with his bubbles. So I have a dish of baking soda. I'm going to pour some vinegar on it to create the gas carbon dioxide. Here we go. I can hear something happening. Carbon dioxide is in the tank. How can I prove that to you? I said carbon dioxide is in this tank, but we can't see it. So how do we prove it's there? Enter my good friend Mitt. Do you remember the last time Mitt blew bubbles into the tank? Well, what did they do? They sank to the very bottom of the tank. I'm going to have Mitt blow some more bubbles in the tank, and I want you to watch carefully what happens to those bubbles. Take a look at this. Mitt's blowing bubbles, and they're not sinking to the bottom of this tank. Why? It's science. There is a layer of gas, carbon dioxide gas, that's actually keeping those bubbles from hitting the bottom of the tank. Remember I said matter takes up space? Well, this carbon dioxide gas is taking up space in the tank. It's actually keeping the bubbles up off the bottom of the tank. Matter takes up space. It's made of stuff. Keep going, Mitt. And they're still there. There's a layer of carbon dioxide gas. It's taking up space. We're going to pile the bubbles in. That carbon dioxide gas actually stayed in the tank because it was heavier than air. But there's also a gas that's lighter than air. Check out these balloons. Watch what happens when I push them down. I push them down, they're filled with helium gas. They take up space, they're taking up space in the balloon. But if it's lighter than air, what's going to happen when I let them go? It should go up. They go up. Gas. You can't see it sometimes, and you can't smell it sometimes, but it's there. And it's matter. It has stuff and it takes up space. Even Mitt knows that. Right, Mitt? That's right. If you want to learn more about gas, check out our links in the video description. Science is so cool.
Now, this chapter is going to deal with gases. Last week's video showed you the beginning, the properties of gases. We're going to continue with those. We're going to go into the gas laws, and we're going to talk about what an ideal gas is. So let's get started. When you talk about gases, gases are compressed. They're easy to squeeze from a large volume into a small volume. When something is compressible, that means it can be taken from a large volume into a smaller volume by putting it under pressure. Because gases can be compressed, the airbag that you have in your cars is used to save your life, because what happens is the gas is formed, it inflates the airbag, and then as the airbag is deflating, your head hits it, which saves your life.
Normally, something blowing up in your face is definitely bad. But right about now, this chemical reaction could very well save your life. It takes 50 milliseconds for you to hit the steering wheel in a crash. Everything we're about to tell you goes down even faster. Your car has to be able to detect when a potentially deadly crash is happening. You don't want your airbag deploying every time you hit a pothole or get in a fender bender. Your car has an accelerometer, several actually, in case one fails or goes off by mistake, that detects sudden, rapid changes in velocity. In one model, a ball bearing is normally held in place by a magnet, but in a crash, it comes flying free, and it flies right into an electrical circuit that tells the car's computer to deploy the airbags. Airbags don't just fill with gas like a balloon blowing up. That would be way too slow. The gas that fills airbags is actually produced by a chemical reaction. The classic example is sodium azide, which is stable until it's heated. In a crash, a small explosive or heating element called a squib goes off and ignites the sodium azide, which decomposes quickly to nitrogen gas and sodium metal. That sodium metal could react with water in the air to produce corrosive sodium hydroxide, so airbag manufacturers include some other compounds to react it into sodium oxide and alkaline silicate instead. By the way, the technology we described is a little old school. Nowadays, most frontal airbags are actually inflated with guanidine nitrate, but it works on the same principle as sodium azide. You're creating a lot of nitrogen gas. And accelerometers have changed with the times too. They're a little more sophisticated than the ball bearing thing. Meanwhile, the nitrogen gas is totally harmless, being the main ingredient in, air. Just a small handful of sodium azide can produce 67 liters of nitrogen. And that volume of gas creates enough pressure to fill the airbag in less than 40 milliseconds. So, quick first law refresher, an object in motion stays in motion. So when your car hits something, it stops, but your body keeps moving forward. And if it keeps moving forward right into the steering wheel or dashboard, that's bad news for you. So the airbag is there to slow you down more gradually than a steering wheel would. But this rapidly inflating cushion isn't actually pillowy soft. The front face of the airbag moves toward you at between 150 and 250 miles per hour. And if you were to hit it while it was still inflating, that might be almost as bad as hitting the steering wheel. To properly slow you down, an airbag has to have blown up already when you hit it. So that means the accelerometer detects the crash, the squib ignites the sodium azide, the nitrogen gas is produced, and in 50 milliseconds, it's already blown up in your face and started to wind down. Between 1987 and 2015, frontal airbags saved 44,869 lives. That's a summer evening at Dodger Stadium's worth of people, and a lot of people around to cheer thanks to one chemical reaction and some ingenious physics. Thanks for watching, and remember to drive safe. This explosion could save your life, but it's still better if it doesn't have to happen. If you like this video, help us make more by clicking here to subscribe and then hitting the bell to get notifications.
Now, the reason why gases can be compressed but liquids and solids can't is because the particles that are in the gas are microscopic, submicroscopic, and they're so small when compared to the overall volume of the gas. The distance between the particles is gigantic when compared to the distances between the particles in a liquid or a solid. So when you put gases under pressure, they can be forced closer and closer together. That's the way that a scuba gear would work, a scuba tank would work. Now I'm going to show you a model. We have two different containers. One's half the size of the other. The amount of particles is the same in both. In the larger container on the left, there are 8 nitrogen blue molecules and 2 oxygen red molecules. So in the larger container, they're further apart. And the particles are always moving. We know that because of kinetic theory. When you place them into a smaller container, the sample is compressed because there's less space between the particles. So if I take it and I take the volume and cut it in half, the volume will then cause the pressure to be doubled.
Another property of gases is that they can be squashed or compressed. Compress the air inside this sealed syringe, let go, and the air expands, pushing the syringe back up. In a gas, the particles are spread out. It's easy to squash them closer together. But release the pressure and the particles immediately move as far apart as possible, pushing against the syringe. Compressed gases can act a bit like springs. This awesome ride at Blackpool Pleasure Beach uses compressed air to catapult its riders to a height of 65 metres in just 2 seconds. As soon as the passengers have been safely harnessed in their seats, their combined weight is measured. It's like a big set of scales. The greater the weight, the more compressed air it takes to launch the riders to the top of the tower. The air is forced into a tank and held under pressure, and then it's ready to go. Other fairground rides use compressed air too. The braking systems of many rides rely on air to stop the cars. You can hear the hiss as the compressed gas escapes. Under normal conditions, gases take up a lot of space. During the Second World War, some cars were converted from running on petrol to running on gas, carried in huge bags on the roof. But it's difficult to carry large quantities of gas like this from one place to another, and let's face it, it looks stupid. Today, gases are transported in high-pressure cylinders. The equivalent volume of 300 cylinders of normal gas can be forced into just one by compressing it. So the cylinders need to be extremely strong. All sorts of gases are stored and transported in this way. Different gases have different uses. Carbon dioxide gas is used to put the fizz into fizzy pop. But how did it get there, and just how much gas is there in a bottle of pop? The gas arrives at the pop factory in huge tankers as liquid carbon dioxide. When CO2 is cooled and compressed, it liquefies and takes up less space. So, 700 tankers worth of gas can fit into just this one. In a totally different part of the factory, the cola drink is being prepared. All the ingredients are mixed together in huge vats. The liquid carbon dioxide is transported around the factory through a network of pipes. It's heated up, turned into a gas, and injected into the flat cola mixture. The bottles are filled and capped immediately to keep the fizz in. Because gases are so compressible, it's possible to squash the equivalent of 8 litres of carbon dioxide gas into this 2-litre bottle of pop. This factory produces 1,500 cans of pop and 250 bottles every minute, so you're talking about a lot of fizz. Just think how much carbon dioxide is trapped in all these.
Now, there are 4 things that we're going to talk about when we talk about pressure of gases. The 4 things we're going to talk about is 1, the number of moles, which is the N, the liters of or volume of the gas, the temperature in kelvins. We're going to talk a little bit about kelvins because it's a different temperature scale than you're used to seeing, and pressure is in kilopascals. So those are the 4 things. So first thing we're going to talk about is what are the 3 things that can affect the pressure? Now there's 4 factors: pressure, volume, temperature, and the amount. Well, the amount is what affects pressure, because if you add more gas, you get more pressure. The volume is going to affect the pressure. The temperature of the gas is going to then also affect the pressure. So let's start with the amount, the moles. We use the kinetic theory and we talk about the fact that gases are constantly moving, and they move in straight lines, and when they move in straight lines, they collide with each other, and when they collide with their container, that's what causes pressure. So if you take an air raft and you start pumping it up with a pump, as you continually increase the volume, you will then also increase the pressure because you're adding more and more gas. What happens inside is the collisions of the particles are then going to cause the pressure on the container so it gets fuller and stiffer as it goes. If you increase the number of particles, which is increasing the amount, you will then increase the collisions, which is why the gas pressure increases. That's why if you blow up a balloon, eventually the balloon will pop because you have too many moles, too much pressure, and it causes it to burst. So here we go. We have a car pump, or I should say a bicycle pump, and we have some gas going into a container. On the left-hand side, you see there's a small amount of gas, has a pressure of about 100 kilopascals. You double the amount, because if you count the number of particles in there, as you double the amount, you double the pressure. If you try to keep adding more and more and more gas, eventually you're going to hit the break point. And when you get to the break point, the container will burst or the balloon will pop. Now, I have a pretty cool video of these Russian guys in a garage, and they overinflate a giant 800-pound tire. Now, there's no sound that goes with this, so I'll just have you guys take a look. You see the guy in the blue coat, and then you guy on the right that's leaning over the tire. Well, that tire is filling with, whoa, it's filling up with air. Well, it nearly fell and hit him. Like I said, that tire weighs, with the wheel, about 800 pounds. The guy on the left is leaving, and the guy on the right is not paying attention, and it hits the breaking point, and it bursts. And as it bursts, it flips the guy over. Luckily, he does not land on his neck, and you can see the cord still attached to the tire, and the tire hits the ground, just missing the guy. If it would have hit him, it probably would have killed him. Now, if you have a sealed container that has a gas inside, two things can happen when you open that container. If the pressure of the gas inside is lower than outside, air will go into the container, sort of like vacuum sealed food. You know, if you put food on a vacuum sealer and you open it, you hear that as it's letting air in. If the pressure of the gas inside is higher than the outside, the gas will flow out, like if you shake a soda. And when you open the soda, it bursts all over the place because the pressure's higher inside. So they're kind of opposite. Aerosol cans are used for many things. You can use them for spray paint, you can use them for glass cleaner, for deodorant, or whatever. But the way it works is simple. You have a pressurized gas that's inside with a propellant. Usually that propellant, as a lot of people know, it's flammable. So the gas propellant could be propane, it could be some kind of other gas, which is under high pressure. When you push down the valve, the pressure allows the gas to, or I should say, allows the liquid to come out, which then the gas wants to expand, because from high pressure it always goes to low pressure. So as it's expanding and the liquid's coming out, the liquid is vaporized or aerosolized, and the gas continues to expand inside. That's why you don't want to turn it upside down, because the tube inside goes to the bottom of the container. Volume. You can raise the pressure of a gas by reducing its volume. They are what we call inversely proportional. As the pressure goes up, the reason it will go up is when the volume is going down. So the more you compress it, the smaller the volume gets, the higher the pressure is. Sort of like when you squeeze a balloon. You are trying to get the balloon to be smaller, which then increases the pressure, which then the balloon will pop because you will go past that breaking point. Raising the volume has the opposite effect. If you take the volume inside a container and you double it by making a container larger, since you have the same number of particles and twice the volume, what happens is the pressure goes down because there's less collisions. So here we have on this slide, a piston can show this thing. If you look at the container on the left, the container on the left has 100 kilopascals pushing down on the piston and 100 kilopascals of the 1 liter amount of the gas. So when you push that from 1 liter to half a liter, since the volume is cut in half, the pressure is cut in two, or I should say it's doubled. They go opposite. As one goes down, the other one goes up. So you'll look, you got 100 to 200, that's doubling. You got 1 liter to a half liter, that's cutting in half. When you change the temperature, just think about temperature is a definite way to tell energy. The higher the temperature, the more energy something has. So as you increase the temperature, the kinetic energy of the particles increases. The faster they move, the more they cause pressure because they're hitting the walls with more energy because they have a higher temperature. For example, if you take the container on the left, we've got room temperature, 27 degrees Celsius, 300 Kelvin. The pressure inside is 100 Kelvin. As you double the temperature in Kelvin, going from 300 Kelvin to 600 Kelvin, which you notice does not match. It doesn't go from 27 to 54. It goes from 27 Celsius to 327 Celsius, which is the difference between them. It's 273. So as it goes from 300 to 600, the pressure goes from 100 to 200. It doubles. If you then try to add more heat, as you see on the right side, instead of using one flame, they have triple the flames. Eventually, when you push the container to its breaking point, it will burst. That's what happens when you put aerosol cans into fires. Now, we're going to do some review. We know when something's squeezed into a smaller volume, we say that is compressed. And the reason why it's compressed, because the space between the particles allows it to be compressed. You have a lot of space and you have very small particles. The four variables, P is for pressure, V is for volume, T is for temperature, and the number of moles is N. The lowercase n is moles. If you want to predict how gases are going to respond by changing any of those four factors, we use the kinetic theory, which shows that particles are moving. So if they're moving at a higher temperature, that's more energy, lower temperature, less energy. By doubling the amount of gas in a container, we'll double the pressure because there's a connection, direct connection between the amount and the pressure. You can raise the pressure by taking the gas and decreasing the volume, because when you have less space, the particles have more collisions. They hit the container with more collisions, which then increases the pressure. As the temperature decreases, the pressure will decrease, because as the temperature goes down, the particles are moving slower. And if they're moving slower, they have less energy, which means less pressure. According to the kinetic theory, the volume of the particles in a gas is small compared to the total volume of the gas. Well, that is the whole thing with the kinetic theory, and that's always true, because we said that the particles themselves are small when compared to the volume of the gas. So when you have gases, sort of like the air in the room, you can't see the particles because they're so small and they're so spread out. Air will rush into a sealed container when it's opened. Well, we just said that if the pressure inside is higher, then the air is going to come out. But we said if the pressure inside is lower, the air is going to go in. So air will only rush in depending on if the pressure inside the container is greater than outside or less than outside. So that's a sometimes thing. Gas flows from lower pressure to higher pressure. No, that's never true. Gases always go from high pressure to low pressure. They're trying to get their energy down, because high pressure is high energy, and things don't like to be under high energy. They like to be spread out. That's why things will explode when you put them in flames, and that's why other things will, when you compress them too much like a balloon, it will pop. Adding air to an object will cause it to inflate. That's also a sometime thing. If it's a balloon that can stretch, yes. If it's a can, like let's say an aerosol can of paint, that's incorrect, because even though you're adding air inside, it's not going to change its volume. The four variables are P, V, T, and N, where N equals moles. That's always true. So that's the beginning of gases. Now we're going to move on to the gas laws. They talked a little bit about those on the video, but I want to really go into the different gas laws, who was involved in creating them, and what each of them deals with. So the gas laws, there are 4 of them that we're going to deal with. The first one is Boyle's law. Boyle's law is a relationship between pressure and volume. If the temperature is constant, that means you can't change the temperature of the gas, and you have the same amount of gas. As the pressure increases, the volume decreases. So the more you squeeze them, the smaller the volume is going to get. And vice versa. If the pressure decreases, the volume is going to increase. So if you put things inside a vacuum, they actually will get larger because there's no air pushing them down. So that's why when you put things into vacuum sealers that have air in them, they will expand. And that's also why when you have weather balloons going up in the sky, when you have lower temperatures, less pressure, less air, and they will expand. Boyle's law states that for a given amount or mass of a gas at constant temperature, you cannot change the temperature for Boyle's law. The volume is inversely proportional to the gas. The equation is P1 times V1 equals P2 times V2. If you look at this and you think of it as simple math, and you have 3 times 2 is 6. Well, if I take the 3, which is my pressure, and I make it a 2, that means the volume has to go up to 3, because 3 times 2 equals 2 times 3, or 6 times 1 equals 1 times 6. So as you think of it that way, pressure and volume are inversely proportional. As one goes up, the other one goes down, and vice versa.
It seems to me like you have decompression sickness.
Decompression sickness? Oh, what's that?
Well, as a certified scuba diver, you should know, but I guess I'll tell you. Also called the bends, you can get decompression sickness from scuba diving without making a slow ascent to the surface. When you're underwater, the water above you is putting pressure on you. The deeper you are, the more pressure is on you, since a larger amount of water is on top of you. Because the pressure is increasing, the volume of air in your gas tank, under your goggles, in your ears, and even in your lungs is decreasing. Such is due to Boyle's law, indicating that volume varies inversely with pressure. It is important to know that the gas in your gas tank is not 100% oxygen. In fact, around 3/4 of the air in your gas tank is actually nitrogen, while other gases, including oxygen, carbon dioxide, argon, and others, use the remaining percent. As the pressure on the nitrogen increases, more of it is absorbed into your bodily tissues. Because it is useless for bodily functions, the nitrogen simply builds up within the tissues. Although the bends can be avoided if you make a slow and steady ascent to the surface, waiting for 5 minutes at 20 feet below to allow the nitrogen pressurized into your system to be released at a steady rate. If you don't make this stop and you ascend too quickly, the nitrogen will rapidly leave the body due to the sudden change in pressure, causing the bends. Depending on the organs involved, symptoms could include pain in and around major joints, fatigue, rashes, the creeps, which is an itching sensation within the skin that has no visible rash, the chokes, which includes burning in the chest, cough, difficulty breathing, and blue lips and skin, and staggers, which is a spinning sensation, deafness, ringing in the ears, and/or vomiting.
I have been having some of those problems. What can I do to fix it?
Well, you'll need to be put in a recompression chamber.
What's that?
It's a sealed space which will return you to the pressure you were at in the water, then slowly decrease to allow the nitrogen to exit your body slowly and easily. However, it may cause you to have nitrogen narcosis, a loss in consciousness due to the anesthetic effect of the gas. We'll have you back out in the open in about 8 hours. You'll also have to come back for up to 30 sessions based on the results of each recompression.
I guess I don't have much of a choice then.
Don't worry, we'll have you all fixed in no time.
So there is a regular example of how Boyle's law works. The next law is Charles' law. Charles' law is comparing the volume and the temperature. So this time we're going to keep the pressure and the amount constant. So Charles' law was developed by taking the volume and the temperature. If you increase the volume, you're going to, what the increase in volume is caused by is an increase in temperature, and vice versa. So if you take a cold day and you have an inflated balloon inside and you take it outside, as you go outside, the temperature goes down. As the temperature goes down, the gases will slow down, which means the volume is going to then decrease. So there is a direct proportion between the Kelvin temperature and the Kelvin volume. So as one goes up, the other one goes up. As one goes down, the other one goes down. Why when the volume goes up, the density goes down. So hot air balloons work in the fact that Charles' law is correct.
How do you not bounce into another balloon? Right? How do you not bounce into another balloon?
Today I want to talk about the turkey pop-up timer. The turkey pop-up timer is a little red and white pokey thing that sticks inside a turkey. These are typically found in store-bought turkeys. If you were to hunt your own turkey and bring it in, then, well, you wouldn't have one of these. Anyway, it goes inside the turkey, and the idea is when you bake the turkey and the turkey reaches a temperature of 165 degrees, the pop-up will pop, and it will basically tell you that your turkey is done. But exactly how does this pop-up timer work? It turns out that all it is a white shell that's shaped similar to an arrow. Then a spring fits inside of that. A pin then gets inserted, pushing down the spring. Then a low melting temperature metal gets put into the bottom of the shell, holding the pin in place. It's not always metal, sometimes it's wax. When this now goes inside your turkey and the inside of the turkey reaches that 165 degrees Fahrenheit temperature, then the metal will actually start to melt and the pin will be released, popping out, giving you the red flag that your turkey is ready for Thanksgiving. This little poppet gives you the perfect turkey every year. So really, you wouldn't have such a perfect turkey without it. Well, not really. You could just use a meat thermometer. But this is much more fancier. Thanks for watching, and we'll see you next week.
So that was an example of Charles' law. The next one is Gay-Lussac's law. Gay-Lussac's law is when you compare the pressure and temperature in a container where the volume will not change. So Gay-Lussac's law is used to tell you that as the temperature goes up, the pressure goes up. Very easy example of Gay-Lussac's law is heating up aerosol cans. So on the left side, we have the container, as always, 300 Kelvin, 100 kilopascals of pressure. When you then heat it up and you double the temperature from 300 to 600, it goes from 100 to 200 because they are directly proportional. It's sort of like 3/5 and 6/10. The same thing. As one goes up, the other one goes up. As one goes down, the other one goes down. So if you were trying to then show Gay-Lussac's law, we would use pressure and temperature are proportional. So you can heat up an aluminum can and then take that aluminum can and place it into a bucket of water and it will collapse. But I got something a little bit bigger than an aluminum can.
760. Gewonnen haben wir Dr.
The whole crowd, what happens is they put the temperature up, and as the temperature goes back down, it then goes down, and since the container is not supposed to collapse, it does collapse because as the temperature goes down, the pressure goes down, which then creates a vacuum, which then sucks in the container using the air outside as a pressure. Pressure cookers are a good way to explain Gay-Lussac's law. A lot of people have their pressure cookers nowadays. In the olden days, like the one you see in the picture, what they did was the pressure cooker was basically a very thick shelled aluminum container with a locking lid, and there's two things on the lid. On the left-hand side is the pressure release, and on the right-hand side is the pressure gauge. Two things that you have to pay attention to if you're using an old school pressure cooker. What happens is inside a pressure cooker, when you cook regularly, the gases will escape, like boiling water and so forth, and the gases escape into the room. Inside a pressure cooker, there's no place for the gases to go. So what happens is it ends up cooking faster because the steam is returned back to the heating food, the meat, the potatoes, whatever's in there. So what happens is it allows the temperature to go higher. So if it's a higher temperature, things are going to cook faster, because what's happening with regular cooking is as you're cooking them, the pressure doesn't change. So the temperature kind of stays the same, because a 350-degree oven is always releasing some of the heat, so it takes longer. So what happens is, as the pressure goes up, the temperature goes up, and since there's no place for the gases to go, it keeps going back in, which then allows you to cut your cooking time. The problem is, as the pressure rises, there's an increased risk of an explosion. If it goes too high, just like we've shown before, the whole container can explode. The combined gas law was taken from Boyle's law, Charles' law, and Gay-Lussac's law, and put them all together because they are all related. Pressure and temperature are directly related, volume and temperature are directly related, and pressure and volume are inversely related. So if you take the three together and the only thing that you keep constant is the amount of gas, you get the combined gas law. So here's a summary of the four gas laws. When temperature and the amount is constant, that's Boyle's law. When pressure in the amount is constant, that's Charles. When volume in the amount is constant, that's Gay-Lussac. And when you only keep the amount constant, meaning you change the pressure, the volume, and the temperature, that's the combined gas law. The pressure and volume of a fixed amount of gas are pressure and volume are inversely related. We said that because as the pressure goes up, the volume goes down, and as the volume goes up, the pressure goes down. Think about it. When you have a smaller volume, you've got more collisions, more pressure. If one decreases, the other one must increase. That's what makes an inverse relationship. As one goes up, the other one goes down. This relationship is known as, with pressure and volume, that's Boyle's law. The volume of a fixed amount of gas is directly proportional to its Kelvin temperature. Kelvin temperature is the temperature, an absolute temperature. Kelvin temperature does not go below 0. 0 Kelvin is the coldest temperature you can reach, and that is when all molecular molecules, or I should say all molecular motion stops. That's at 0 Kelvin. It is a theoretical degree. You can't actually reach it. So then we say the relationship is known between the volume and the temperature. That's Charles' law. The law that states the pressure is proportional to temperature is Gay-Lussac's law. And the Gay-Lussac's law states the pressure is directly proportional to the temperature. And that's only if the volume stays the same. So that's Gay-Lussac is used for aerosols. That's the best way to remember that one. These three separate laws can be written as a single expression, which we call the combined gas law, which can be used if only the amount is kept constant. So we didn't do any of the gas law calculations. There are several ways to do them. If you take physics, they'll go into the gas laws and you'll do the different pressures and volumes and temperatures and such, and you'll get to do all those calculations. Here, because I'm just introducing it to you, basically we're just learning the names. We're not going to go into it. Just realize that if you want to remember, pressure and volume are the only ones that go opposite. Temperature and pressure, temperature and volume all go the same way. So as the temperature goes up, the pressure goes up. As the temperature goes up, the volume goes up. But as the pressure goes up, the volume goes down. If you can just remember that, you can then easily go through the laws. The last one is the ideal gas law. The ideal gas law was created by taking all the gas laws and moles and placing it into one law, and it's called the ideal gas law. If you look at the top, the way that most people look at the gas law is PV equals nRT, where P is pressure, V is volume. That's really basically Boyle's law. And then nRT, N is the amount, T is temperature, and R is something we're going to learn in this section called the ideal gas constant.
The combined gas law is great. We can manipulate pressure, volume, and temperature. But what about moles of a substance that we're using? Before we add moles to our equation, we need to figure out what the relationship is with other variables and find out if the identity of each gas matters. Because of Avogadro's hypothesis, equal volumes of gases at the same temperature and pressure have the same number of particles. This means the identity of the gas will not matter, just the number of moles. As you increase the number of atoms in a balloon by, say, blowing air into the balloon, the volume increases. The pressure is the same because the balloon can expand and the temperature is the same. So moles and volume have a direct relationship. Since volume and moles are directly related, just like volume and temperature are directly related, we can put the number of moles, or N, next to temperature. But now we're holding nothing constant, so let's hold one entire side constant by setting it to the STP values, and we'll call it R. And we can get rid of the division by multiplying on both sides. And you don't need the subscripts anymore either. And you get PivNert, the ideal gas law. Pressure times volume equals moles times a constant times temperature. So much beauty in such a small mathematical equation. Let's talk about what R is exactly. Remember, the R value is created from the equation set to STP values. So we plug in the values of pressure, the volume of a mole at STP, and the temperature at STP. And we get our results, like this one, 8.31 kilopascal liters per Kelvin mole. But there are different R values for different pressure values, so make sure that you check your problem to see which units you need to use. At what pressure would 0.150 moles of nitrogen gas at 23 degrees Celsius occupy 8.9 liters? We're going to use PivNert here, and since we're trying to find pressure, we'll rearrange the equation to get pressure by itself. Now we just need to actually plug in our data. When it comes to choosing which R value to use, it's actually up to you in this case, since no specific unit of pressure was requested. I'm going to use 8.31 kilopascal liters per Kelvin mole because kilopascal is the SI unit. Now, don't forget, you need to turn Celsius into Kelvin whenever you're doing mathematical problems. Divide by the liters, and your final answer will be 41.5 kilopascals. Now, the ideal gas law makes some assumptions about ideal gases, so let's compare ideal gases to real gases. Ideal gases have no volume, but of course that isn't the reality. Real gases do have volume, and that will play a role in how it actually behaves. Ideal gases have no molecular attractions, but real gases are attracted to each other. In fact, when they cool down, they stop being gases and will form liquids and solids because of their attractions. Ideal gases follow the gas laws at all pressures and temperatures, and real gases will differ at low temperatures and high pressures. So basically, there's no such thing as an ideal gas. But real gases behave like ideal gases in many conditions. This is why we can still use PivNert, the ideal gas law.
Now, if you look at this set of values for real gases versus ideal gases, let me first calm you and realize that we're not going to be doing the calculations that she just showed. The main thing I wanted you to see was, yes, you can plug all these in to solve for pressure, volume, moles, temperature. As long as you have the other values and you have the correct use of R, you can do that. But the main thing is ideal gases, if it's considered an ideal gas, is the volume is completely the volume of the container, as if the volume of the gas doesn't count. But we all know that real gases have volume because otherwise we wouldn't be breathing right now. There's no molecular attractions in ideal gases, but real gases do actually attract each other and repel each other. They follow the gas laws for ideal gases at all temperatures, pressures, where if you're talking about actual gases, they differ at low temperatures because at low temperatures, the gases will actually turn into liquid, and at very high pressures, you can pressurize the gas to turn it to a liquid or even a solid, as in the way of, let's say, dry ice, which is solid carbon dioxide, which is formed by just putting carbon dioxide under very high pressure. So, in addition to pressure, temperature, and volume, which we were dealing with the ideal gas laws, the fourth value that must be considered when analyzing a gas is N, right there, N, which is the moles. Moles is what chemistry uses for their counting. It's their amount. It is very important in chemistry, and if you take a chemistry course in the future, you will be talking a lot about moles. The number of moles in a sample is directly proportional or inversely proportional to the number of particles. Well, it's directly proportional because it really is just the number of particles, because when you talk about particles, that's an amount, and you talk about moles, that's an amount. So it really is just talking about the number of particles in a normalized way. When you talk about chemistry, we use moles because molecules are so small. At a specified temperature and pressure, is the number of moles directly proportional or indirectly proportional to the volume? Well, since V is on one side and N is on the other side, well, if V is 5 and N is 5 and V is 6, then N would be 6, so they're directly proportional, because when things are equal to each other on opposite sides of an equation, as one goes up, so does the other one. The letter that best describes how you're going to take the combined gas law and modify for the number of moles. Well, multiply each side by the number of moles. No, that's not what they did. Add the number of moles to each side. No, there's no addition in that equation. Divide each side by the number of moles. So here we go. There is the combined gas law. P1 V1 over T1 equals P2 V2 over T2. Pressure times volume divided by temperature equals pressure times volume divided by temperature. If you change them, they're equal to each other, so as one goes up, the other one goes up if you're talking about volume or temperature, and pressure and volume are inverse. So if I want this to work, I'm going to then put the moles on the bottom. So when I put the moles on the bottom, that then, if you look up top, PV equals nRT, if you take them and move them around algebraically, then moles end up on the bottom of this equation. For what kind of gas does PV over T times N, a constant for all values of pressure, temperature, volume under which the gas can exist? Only for ideal gases. And remember, ideal gases are just so you can plug them into the equation. There are always some interactions, there's always some size problems that happens when you have large amounts of gases. But for the most part, gases will act ideally. Number 6, what constant can you calculate when you know the volume and you know that you have 1 mole and you know you have standard temperature and pressure? Well, that's going to be R, which is the gas constant, which you see below. If you take pressure in standard pressure, volume, 22.4 liters, temperature, 298 K, moles, 1. And when you get that, you can then get the 8.31 kilopascals times liters divided by K times mole, or any of the others that were explained just previous. So if you know what you're trying to do, and you know that R is the thing, using liters for the volume, using pascals for the pressure, using Kelvin for the temperature, and moles, of course, for moles, instead of it looking like below where it's kilopascals, liters, K times mole, it's just pascals and liters. You can use different values depending on what's given in the problem. And last but not least, if I'm looking at this, P is pressure. The unit for pressure, kilopascals. The abbreviation is kPa. V is volume. The unit is liters, and it's a capital L. N is the amount, the moles. The amount is moles, and the abbreviation is MOL. Don't ask, it's just MOL. R is the gas constant. Using what we have, it's liters times pascals divided by K times mole, or any of the others, as long as you change the volume or you change the pressure. The Kelvin stays the same, mole stays the same, and the liters times pascals divided by Kelvin per mole is the same. T is temperature. Temperature must be in kelvins, and the abbreviation is K. And when would we use the ideal gas law instead of the combined gas law? That's if we want to calculate moles. All right, one more worksheet. The ideal gas law permits you to solve for the amount of a contained gas when the pressure, volume, and temperature are known. The ideal gas law describes the formula as PV equals nRT or moles equals PV over RT. The ideal gas law describes by the formula N, where N is the moles, and the gas R, the letter R, is the ideal gas constant. R is equal to 8.31 liters times kilopascals over moles times K. That's using the standard units for everything. So number 6, a gas conforms to the gas laws at conditions of temperature and pressure, and that has to be considered an ideal gas. But no real gas behaves ideally at all temperatures and pressures. As I said, as the temperature gets too low or the pressure gets too high, they start to break down. That's what we call deviations. Deviations from the ideal gas at high pressures, because they're so close together, because the volume would be very small at high pressures. And we use that because that's intermolecular attractions. When you get them so close together, they're going to have to interact between each other. And if there's intermolecular attractions between the particles, and the particles actually have volume, because you have to realize that they have to have volume or they're not matter. So they do have volume, so eventually the pressure and the temperature are going to cause them to deviate from the PV equals nRT. But in normal conditions, we never have to deal with that. Last but not least, the ideal gas law allows you to solve for the number of moles of a contained gas when pressure, volume, and temperature are known. Of course, A, that's always, because that's why the ideal gas law exists. The ratio of P times V over R times T is equal to 1 for real gases. Sometimes it is equal to 1 for real gases depending on if you're talking about low temperatures or high pressures, then it's not equal to 1. Number 12, the behavior of a gas is most likely to approach ideal behavior at high pressure, low temperature. That's never true. That's when they will definitely not behave ideally. That's when they will deviate from the ideal gas law. Number 13, for an ideal gas, pressure and volume are directly proportional to each other when all other factors remain constant. That's false. No matter if you're talking about an ideal gas law or you're talking about Boyle's gas law, pressure and volume are inversely proportional. As one goes up, the other one goes down. Directly proportional, we say as one goes up, the other one goes up. And last but not least, number 14, the number of moles is directly proportional to the number of particles. That's always true, because as I said, the number of moles is really just an indicator of the number of particles. Thank you, and make sure you complete the assignment for the week.